A construction crew is cutting through a Pennsylvania hillside in the summer of 1956, carving out what will become Interstate 80. A massive bulldozer shoves a boulder across freshly turned earth, while the operator wrestles with two long steel control levers. Behind him, mechanical systems powered directly by the diesel engine are controlling that 6-foot blade. No hydraulic fluid, no computer assistance, no backup systems, just a direct mechanical connection between the operator's hands and the blade doing the work. One mechanical failure away from serious problems. And this was standard across every construction site in America. These machines built the highway system you drive on today, cleared forests that became suburbs, and moved billions of tons of material in mines and quarries, using technology that seems impossibly crude by modern standards. How did operators control these massive machines? Why was the work so physically brutal? And what finally pushed the construction industry toward the equipment we use today? Let's talk about what construction equipment was actually like before modern hydraulic systems became standard. If you have watched modern bulldozers work, everything looks effortless. The operator moves a joystick, the blade responds smoothly, and the machine does exactly what is commanded. Go back to the 1940s and the 1950s, and the reality was completely different. These machines used direct mechanical systems connecting the operator's control levers to the blade through a series of mechanical components. The diesel engine that powered the tracks also powered a winch assembly behind the operator's seat. This winch had large rotating drums that controlled blade position. When you pulled back on a control lever, you were engaging mechanical clutches and brakes that controlled these drums. You could push the blade down into the dirt, pull it back up, angle it left or right, all through direct mechanical manipulation. No power steering, no hydraulic assistance, just the operator's strength and constant attention. What made this system work at all was the direct feedback it provided. When that blade hit something solid buried in the ground, the operator felt it immediately through the control levers in their hands. Modern equipment tries to replicate this with sensors and computers, but vintage machines gave you a physical connection to what was happening. Experienced operators talk about being able to tell what kind of soil they were working in just from the vibration patterns transmitted through those levers. That sounds almost mystical until you understand they were doing this work 8 to 12 hours a day, 6 days a week. Your hands learned things your brain never consciously processed. Now you are probably wondering why construction equipment worked this way. Hydraulic technology existed in the 1940s. Why not just use that instead of these complex mechanical systems? The answer comes down to reliability under actual working conditions. Early hydraulic systems had a serious problem with seal technology. The rubber seals that kept hydraulic fluid contained could not handle the combination of high pressure, extreme temperatures, and constant movement required in construction equipment. A hydraulic system might work fine in a factory test environment with controlled conditions. Put that same system on a bulldozer working in summer heat or winter cold, moving a blade through rocky soil for 10 hours straight, and those seals would fail within days or weeks. Hydraulic fluid would leak out, the blade would lose pressure and drop, and the machine would be down until someone could repair or replace the failed components. For a construction company in 1948 working on a highway project in the mountains, the nearest equipment dealer might be 200 miles away. A hydraulic failure meant the machine sat idle for days or longer, waiting for parts, and a technician who knew how to rebuild the system. The mechanical systems these vintage machines used could be repaired by any competent mechanic with basic tools. Components wore out or broke. You could fix them on site with wrenches, replacement parts that were simple to source, and practical mechanical knowledge. That reliability difference was decisive for contractors who needed equipment working every day. The other major advantage was simplicity of maintenance and repair. The mechanical components were familiar. rotating drums, mechanical clutches, and basic machine elements that had been used in industrial equipment for decades. There were no precision-machined hydraulic cylinders requiring specific tolerances, and no hydraulic pumps with complex internal valving. When something needed attention, the mechanic could see the problem, understand what was wrong, and fix it with straightforward procedures. For construction companies working in remote locations, logging operations deep in forests, and mining companies miles from the nearest town, this meant the difference between equipment that kept running and machines that sat idle waiting for specialized help that might never arrive. If you are finding this look at construction history interesting, hit that like button. We are covering how things actually worked in an era most people do not think about, and your support helps justify the research time. So where were these machines actually working? The answer is basically everywhere construction happened in America from the late 1930s through the 1960s. Highway construction was probably the single biggest application. When the interstate highway system was authorized in 1956, it required moving literally illions of cubic yards of earth. Mountains needed to be cut through, valleys had to be filled, grades established for hundreds of miles of new roadway. The construction crews doing this work used fleets of bulldozers that operated the way we have been describing. You would have multiple machines working together, cutting into hillsides, pushing material over edges to create fill areas, establishing the roadbed that would eventually become the highway surface. The operators on these highway projects became incredibly skilled because the specifications were tight. If you were cutting a roadbed and went 6 inches too deep in one section, you would have to bring in additional material to correct it. Good operators developed an almost instinctive sense for blade position, making tiny adjustments constantly to maintain the grade without needing surveyors checking their work every few minutes. Logging operations in places like the Pacific Northwest, throughout Canada, and in Scandinavia represented another massive use of this equipment. Bulldozers working in forest environments often had additional mechanical systems for dragging felled trees to collection points, but the basic blade control worked the same way. The conditions in logging were brutal. You were working on steep slopes, in mud when it rained, and over terrain covered in tree stumps and woody debris. The mechanical systems these machines used were actually ideal for this environment because they were exposed and simple. Modern hydraulic lines running across the machine would get torn up by branches and rough terrain. The mechanical components could take abuse that would destroy more sophisticated systems. Operators would push over trees that were in the way, rip out stumps, and create improvised roads through forests that had never seen machinery before. The equipment took incredible punishment and kept working because the systems were fundamentally robust. Mining operations and stone quarries needed heavy equipment for moving overburden, the worthless rock and soil covering the valuable material they were actually mining. Bulldozers would push this overburden to the edges of open pit mines, creating the terraced appearance you see in mining photos. This work did not require the precision of highway construction. You were just moving large volumes of material efficiently, but it required power and reliability, often in locations far from support services. Desert mines in Nevada, copper operations in Arizona, coal mines in Appalachian regions. These were places far from equipment dealers and parts suppliers. The mechanical systems earned their keep in these environments because one mechanic could keep them running without needing factory-trained technicians or specialized replacement parts. Agricultural land clearing expanded dramatically after World War II as farming became more mechanized. Converting forest land or brush into productive cropland meant removing trees, pulling stumps, grading fields to proper drainage, and excavating farm ponds and drainage ditches. Farmers who could afford to purchase or lease a bulldozer could dramatically expand their productive acreage. These machines were preferred for agricultural work because farmers and farm mechanics could maintain them using the same skills and tools they applied to tractors and other farm equipment. Photos from the 1950s show individual farmers with a single bulldozer clearing land that would have taken crews with hand tools months to accomplish. The economic impact was enormous, enabling the expansion of mechanized agriculture that helped feed the post-war population boom. Yes, military construction battalions used this equipment extensively during and after World War II, building bases and airfields around the world. But the military application was just one among many, and the civilian construction work represented the vast majority of the working lives of these machines. This equipment was not primarily military. It was a fundamental tool of economic development and infrastructure expansion. But operating these machines was nothing like running modern construction equipment. This is where you start to understand why the work was so physically demanding. Modern bulldozer controls are almost effortless. You move a joystick with light finger pressure, hydraulic systems do all the work, and the blade moves and holds position automatically. Hydraulic pressure maintains blade height even when you encounter varying resistance in the soil. With the mechanical systems we are discussing, everything was dynamic and required constant operator input. Blade position was maintained through the balance between mechanical forces pulling the blade up and the blade's own weight pulling it down. If you wanted to hold the blade at a specific height while moving forward, you had to constantly adjust the mechanical controls to compensate for changing loads as the blade encountered different soil conditions. Hit a section of soft ground, the blade would start to sink and you needed to adjust. Hit hard compacted material, the blade would try to ride up and you needed to compensate the other direction. This adjustment was continuous throughout the entire working day, and it was exhausting. Operators would finish 8-hour shifts with their forearms and hands literally cramping from the precise control effort required. The control levers were not light either. You were manipulating mechanical clutches and brakes that were controlling systems under significant load. Some experienced operators developed techniques using their body weight and legs to help manage the levers, but it remained physically demanding in a way modern equipment operation simply is not. There is a reason experienced operators were highly valued and well paid for the era. The skill curve was steep. A novice operator would be jerky and inefficient, would stall the engine by overloading the blade, or would lose control and end up with the blade in positions that jammed the system. An expert operator made it look easy, flowing smoothly over terrain with constant small adjustments that kept the blade working at maximum efficiency without overloading the engine. That level of expertise took months or years to develop. You could not just put someone in the seat and expect competent results. The mechanical systems themselves required constant attention and maintenance. The components would stretch and wear under the enormous loads they were handling. This meant that blade height and angle calibration would gradually drift over time. Operators had to compensate by making adjustments, essentially recalibrating as they worked. After equipment had been operating for hundreds of hours, components would need adjustment or replacement to restore proper function. This was not a sign of failure. It was just the nature of mechanical systems under heavy cyclical loading. Equipment inspection was critical and required knowledge that had to be taught. The mechanical components did not fail suddenly from perfect condition. They degraded gradually as parts wore. You could have systems that looked fine from casual observation, but were actually compromised and close to failure. Standard inspection procedures involved checking multiple points on the equipment, looking for signs of wear or damage that indicated components needed attention. More than a few warning signs visible during inspection meant components needed replacement before catastrophic failure occurred. Ignoring equipment condition was asking for serious problems. Component failures under load could cause violent mechanical reactions. There are documented cases of catastrophic failures causing serious injuries or fatalities to workers near the machines. Modern equipment has multiple safety systems to prevent injuries. These vintage mechanical systems obeyed the laws of physics. When something failed under load, the results could be deadly. Subscribe if you are getting value from this deep dive into construction history. We are covering the engineering and equipment that changed how we build things, and there is more vintage construction content coming. Every point where mechanical components interacted was a potential wear location. These connection points were mounted on the equipment frame in positions that got exposed to all the mud, dust, rocks, and debris the machine kicked up during operation. Bearings and moving parts would accumulate grit, which caused increased friction and accelerated wear. Maintenance schedules called for regular lubrication of every moving part, typically every 8 hours of operation. In practice, especially on busy construction sites with tight deadlines, this interval often got stretched or skipped. The consequence was accelerated wear and increased risk of failures. Good maintenance practices demanded that mechanics go over machines systematically at the end of each shift with lubrication equipment, servicing every bearing and moving part. It was tedious, time-consuming work, but skipping it led to expensive component replacements and potential safety incidents when parts failed unexpectedly. Weather conditions added another layer of complexity to equipment operation. Cold temperatures affected how mechanical components functioned. Metal becomes more brittle as temperature drops, and moving parts that worked smoothly in warm conditions could behave differently in extreme cold. Operators in northern climates learned to be cautious with equipment in winter. You would warm the engine slowly, make gentle initial movements, and avoid sudden loads on the mechanical system's hardware until the machine had been running long enough to reach stable operating temperature. Even with careful operation, winter work was inherently more risky. Construction projects in states like Montana and Wyoming would experience frequent mechanical issues during winter months, despite operators following best practices. The alternative was shutting down all winter, which was not economically viable for most contractors, so they accepted the increased risk and kept spare components on hand for quick repairs. Hot weather created different challenges. Extreme temperatures in desert environments or during summer work in southern states would accelerate wear on moving parts because lubricants would break down faster. Dust was also significantly worse in hot, dry conditions. Construction equipment generates enormous dust clouds when working in dry soil, and that dust infiltrates everywhere. Mechanical systems, being largely exposed rather than sealed, would accumulate dust that acted like an abrasive compound when parts moved against each other. This accelerated wear on both moving components and their bearing surfaces. Some operators in dusty conditions would apply additional lubricants more frequently to help manage the dust. But this was at best a marginal improvement. Muddy conditions created their own set of problems. Wet, sticky mud would accumulate on exposed mechanical parts and in gaps between moving components. While this did not usually cause immediate failure, it added resistance and drag to the systems, which meant the operator had to work harder to achieve the same blade movements. Mud infiltrating into precise clearances could also cause mechanical bindings that jammed systems entirely. Clearing mud from mechanical components meant shutting down and manually cleaning parts, which cost productive time. Some construction jobs were inherently muddy. For example, spring building season in areas with clay soil, logging operations during rainy seasons, and any work in areas with high groundwater or near streams. The mechanical systems worked in these conditions, but they required more frequent maintenance and were more prone to problems than work in dry conditions. Safety culture around construction equipment in the 1950s was fundamentally different from modern standards, which is a polite way of saying it was often inadequate or non-existent by today's measures. These machines had no rollover protective structures, No seat belts because there were no enclosed operator cabs. No backup alarms to warn people when equipment was reversing. And no proximity sensors to detect workers in dangerous positions. If you walked behind a bulldozer and the operator did not see you, you could be run over. If a mechanical system failed violently and you were in the wrong location, you could be injured or killed. The operating philosophy was essentially that it was each worker's individual responsibility to stay clear of known hazards. Modern equipment design operates on the assumption that mistakes and lapses in attention will inevitably occur, and the equipment should have systems in place to protect people when those mistakes happen. Equipment from the cable era was designed with the assumption that trained workers would not make serious mistakes, and if they did, the consequences were their responsibility. That sounds harsh by contemporary standards, but if you look at industrial accident statistics from the 1940s through the 1960s, construction was among the most dangerous occupations in America. Equipment-related fatalities were common enough that they barely made the news unless multiple people died in a single incident. If you are still watching at this point, hit that subscribe button. This kind of deep historical content does not pull massive numbers, but the people who appreciate it really value it, and you are probably one of them. Given all these challenges and limitations, why did mechanical systems dominate construction equipment for so long? If hydraulic technology offered potential advantages, why did it take until the 1960s for hydraulic systems to fully replace the mechanical approach? The answer is simple: proven reliability. Hydraulic technology had to improve enough to overcome the proven reliability of mechanical systems, and that development took longer than you might expect. The key breakthrough was in materials science, specifically the development of synthetic rubber compounds that could maintain their sealing properties across extreme temperature ranges while resisting degradation from contact with hydraulic fluids. Early rubber materials, both natural and first-generation synthetics, would become brittle in cold weather and soft in hot conditions. They would swell and degrade when exposed to petroleum-based fluids. They would develop cracks and lose sealing ability after relatively few pressure cycles. By the mid-1950s, chemical engineers had developed specialized elastomer compounds that could handle temperatures from -40 to +300 degrees Fahrenheit, resist mineral oil and synthetic hydraulic fluids, and survive millions of pressure cycles without degradation. This made hydraulic cylinders viable for the multi-season, multi-year service life that construction equipment demanded. The second major factor was improvements in manufacturing precision. Hydraulic cylinders require very tight tolerances between the piston and the cylinder bore to prevent hydraulic fluid from bypassing the seals and causing pressure loss. During World War II and the immediate post-war period, manufacturing was necessarily focused on speed and production volume. Precision tolerances were often sacrificed because tighter tolerances meant slower production and more expensive tooling. By the mid-1950s, peacetime manufacturing could prioritize quality and precision over raw volume. Hydraulic cylinders could be manufactured with the accuracy needed for reliable long-term operation. This precision manufacturing capability also extended to hydraulic pumps and control valves, which contained complex internal passages and moving parts that required accurate machining to function properly. The third factor, often overlooked in technical histories, is that hydraulic systems enabled capabilities that mechanical approaches simply could not match. Once you had hydraulic power available on the machine, you could run additional hydraulic circuits to power supplementary attachments. Want to add a ripper to break up hard rocky ground before the blade pushes it? That needs hydraulic power. Want a hydraulically powered winch for pulling operations? Hydraulics. As construction equipment evolved from simple, single-function blade machines into multifunction tools capable of various operations, hydraulics became necessary just to power all the additional capabilities that customers increasingly demanded. The mechanical systems we have been discussing were fundamentally limited to basic blade control. You could not easily branch mechanical power to run multiple auxiliary systems. But even with these significant advantages becoming available, the industry transition was not instantaneous. Mechanical systems were proven technology backed by decades of successful field experience. Contractors who had been running mechanical machines successfully for years were not eager to switch to new hydraulic technology that might have unforeseen problems or reliability issues. Hydraulic equipment was also more expensive initially. The hydraulic pumps, cylinders, hoses, and control valves added cost that mechanical systems did not carry. For price-conscious buyers, especially in demanding industries like logging and mining, where equipment took extremely heavy abuse, the extra initial cost of hydraulics was a difficult sell unless manufacturers could clearly demonstrate better productivity or significantly lower operating costs that would offset the higher purchase price. Major equipment manufacturers like Caterpillar handled this industry transition very carefully. They did not simply announce that mechanical systems were obsolete and force customers to switch immediately. Instead, they introduced hybrid machines that combined proven mechanical components with new hydraulic systems. One common approach used mechanical systems for primary blade lift, which handled the highest loads and was the most critical function, while adding hydraulic systems for blade angling, which required less force and was less critical if it occasionally malfunctioned. If the hydraulic angling system failed on a job site, an operator could manually set the blade angle and still complete most work using just the mechanical lift controls. This hybrid design approach continued for several years as hydraulic reliability steadily improved and customers gained confidence in the new technology. By the early 1960s, fully hydraulic machines had proven reliable enough that mechanical systems were gradually phased out of new production. The last purely mechanical bulldozers rolled off production lines around 1961, though many of these machines remained in active service for years or even decades afterward, because they were still functional and paid for. What happened to all those mechanical bulldozers once they were eventually replaced by hydraulic equipment? Some ended up in scrap yards, cut apart for steel when scrap metal prices were favorable. But a surprising number continued working in specialized applications where their limitations were not critical, or where their mechanical simplicity was actually an advantage. Alaska and northern Canada in particular became final operating locations for many mechanical machines. Remote mining operations, logging camps, and construction projects in areas accessible only by barge or aircraft often had mechanical bulldozers that had been working there for decades. These machines kept running because they were already on site. They still functioned adequately for the work, and the cost of transporting replacement equipment would exceed the value of having slightly more modern capability. There are documented cases of machines built in the 1940s still performing work in Alaska in the late 1970s, more than 30 years after they were manufactured. The harsh environmental conditions actually favored mechanical systems in some ways, because hydraulic fluid becomes extremely thick and viscous in extreme cold, making hydraulic equipment difficult to start and sluggish to operate until it warms up to reasonable temperature. Mechanical systems functioned regardless of temperature, as long as the diesel engine would start and run. Like this video if you appreciate the depth here. There is more content coming on the engineering and equipment that built the 20th century, and we need to know there is an audience for this material. The engineering principles behind these mechanical systems show up in unexpected applications today. Modern logging equipment used for steep slope forestry operations still employs similar mechanical principles because they are simple, powerful, and maintainable in remote locations. The fundamental concepts have not changed. Direct mechanical connection under tension remains one of the most reliable methods for transmitting large forces across distance in harsh environments where sophisticated systems would fail. Offshore drilling platforms use mechanically suspended equipment for similar reasons. When you need to lower tools thousands of feet below the ocean surface, direct mechanical systems prove more reliable than complex hydraulic or electronic alternatives. Even theatrical rigging systems, used for raising and lowering stage curtains and scenery, often employ similar mechanical principles because they are inherently fail-safe in ways that powered systems are not. If electrical power fails, mechanical brakes hold load safely. Compare that to hydraulic or purely electric systems that might fail in dangerous ways during power loss. There is something philosophically interesting about mechanical systems that is worth considering. They represent a fundamentally different engineering approach than modern technology embodies. Today's engineering philosophy emphasizes control and precision. We design systems that do exactly what operators command, with minimal physical effort required from the human. The mechanical bulldozers we have been discussing represented the opposite approach. They provided rough control that required constant physical engagement from the operator. But that direct mechanical connection meant operators understood their machines in a visceral, physical way that is largely lost with modern technology. When you can feel every rock transmitted through the control levers in your hands, when you learn to judge loads and soil conditions by subtle vibration patterns, you develop a relationship with equipment that is more similar to riding a horse than it is to driving a modern car. Today's equipment operators are more like aircraft pilots, monitoring computerized systems, than traditional craftspeople directly wielding physical tools. Neither approach is inherently better or worse than the other. They are simply different philosophies. But something genuine was lost when we eliminated direct mechanical feedback in favor of hydraulic isolation and electronic mediation. The loss of direct, tactile connection changed how operators experienced their work. The safety improvements that came with modern hydraulic equipment are undeniable, and they should not be minimized. Contemporary construction equipment is dramatically safer than mechanical-era machines. Enclosed operator cabs with rollover protective structures, mandatory seat belts, backup cameras that provide visibility in blind spots, proximity sensors that detect workers in dangerous positions, and automatic engine shutdowns. If the operator leaves the seat, all these features save lives and prevent serious injuries. These are real safety gains. Those same safety systems also distance operators from the work in ways that fundamentally change the nature of the job. An operator running mechanical equipment was physically exposed to the environment, directly engaged with the work, and constantly aware of surrounding hazards because personal survival depended on maintaining that awareness. A modern operator sits in a climate-controlled cab with radio and mobile connectivity, surrounded by sensors and automated warning systems. The job is unquestionably safer and far less physically demanding, which is genuine progress that benefits workers. But it has also evolved into something more similar to operating a video game representation than directly manipulating physical tools to accomplish work. Some veteran operators who worked with both mechanical and modern hydraulic equipment talk about missing aspects of that direct connection to the work, even while acknowledging they do not miss the physical exhaustion or constant danger. What lessons from mechanical construction equipment remain relevant today? Perhaps the most important is that the best technology is not necessarily the most advanced option available. It is the technology that works reliably under the actual conditions where it will be used. Mechanical systems dominated construction for 30 years, not because engineers were unaware of alternatives, but because mechanical approaches worked when early hydraulic systems proved unreliable. Mechanical machines were repairable using basic tools by people with practical mechanical knowledge. rather than requiring specialized training. They did not require perfectly clean fluid, perfectly sealed systems, or extremely precise manufacturing tolerances to function adequately. They traded operator convenience and control precision for ruggedness and repairability. In operating environments where those trade-offs made economic sense, mechanical systems were legitimately superior to early hydraulic alternatives. Only when hydraulic technology improved enough to match mechanical reliability while simultaneously adding genuine functional advantages did the industry transition make economic sense for most users. That principle remains relevant to any discussion of new technology replacing established approaches. New technology has to actually perform better under real-world operating conditions, not just in theory or under idealized laboratory testing. There is also a meaningful lesson about complexity versus understandability in failure modes. Mechanical systems had obvious, readily understandable failure modes. Components broke or wore out in ways that were visible and predictable. Modern hydraulic and electronic systems can fail in much less obvious ways. Sensor drift, software glitches, and contaminated hydraulic fluid can cause strange equipment behaviors that are difficult to diagnose without specialized knowledge and testing equipment. Repairs often require specialized tools, proprietary diagnostic software, and factory-trained technicians. In some important ways, we have traded straightforward mechanical failures that anyone could understand for complex systemic failures that are significantly harder to diagnose and repair. This isn't an argument that older technology was superior. Modern equipment is clearly more capable and productive. But it's worth recognizing and acknowledging what was traded away in exchange for those improvements. The mechanical bulldozers that dominated construction from the 1940s through the early 1960s were brilliant engineering solutions to the technical challenges of their era. They moved the earth that built the interstate highway system, cleared the forests that became post-war suburban developments, excavated the mines that supplied industrial raw materials, and performed thousands of other tasks using nothing more sophisticated than direct mechanical connection and operator skill. They were dangerous to operate, physically exhausting, and extremely limited in capability compared to modern equipment. But they worked. They worked reliably in harsh conditions that would have destroyed early hydraulic systems. They were maintainable by ordinary mechanics without requiring factory support or specialized parts. For their time, and given the available alternatives, they were exactly the right technology for the job. The fact that we have moved beyond them does not diminish their historical importance or the cleverness of their engineering design. It simply means that technology advanced to the point where clearly better options became available and economically viable. That is fundamentally how technological progress actually works in practice, not through revolutionary replacement of functional technology, but through gradual improvement and refinement until new approaches become demonstrably superior. These mechanical construction machines earned their place in history by accomplishing essential work during an era when no better alternative existed. That is ultimately all any technology can legitimately claim to have achieved.